Welcome students. Again chapter number 4, video number 25. In this video, we will discuss about Ampere's circuitial law, okay, and about solenoid. Let us say. What is Ampere's circuitial law? So it is very similar to that alternative of that Biot-Savart law. Okay, and Ampere's circuitial law is for open surface. Okay, let us see what is it. As shown in figure, consider these are the electric current passing through this surface. So it is the direction of electric field from left to right. So it is electric field. Okay, here you have to consider one surface. Okay, so we have considered one surface. So this is the surface. Got it? So according to that right hand thumb rule, electric current is in this direction and magnetic field is tangent to the direction of electric current. So this is the direction of magnetic field. Okay, for this surface, consider line element of length dl. So for this line element, magnetic field is given by B multiplied by dl. But if we want to take this line element for entire surface, then you have to take integration. So integration entire surface become a closed loop. So close integration of B dot dl means close integration of magnetic field for all line element, that is dl, is equal to mu 0 times electric current passing through the surface. Okay, so this equation is equation of Ampere's law. Got it? Again, from this, it having a statement okay, what is the statement? That is close integration of magnetic field for any surface is mu 0 times electric current. Okay, that is closed integration of B, that is magnetic field dl, line element of any surface, and here for any surface you have to take its length element is equal to is equal to mu 0 times what? I, that is electric current passing through the surface, passing through the loop. So it is its statement. Clear? Now there are special cases. Let us take case number 1. If you want to find that Ampere circuital law for a infinitely long conducting wire. So this is case number 1. That means if we are taking infinitely long conducting wire. Okay, so this infinitely long conducting wire having a length. Which length? That is capital L. Okay, so our equation become B multiplied by closed integration of dl is equal to mu 0 I. Got it? So closed integration of small lengths, it is nothing but total length. So it is B multiplied by L is equal to mu 0 I. From this, make a subject B. So B is equal to mu 0 I by L. Okay, so this equation is for infinitely long conducting wire. Here we took L, that is the length, either it is small or capital, but we have to remember that now L is the length of total length of a wire, and from this equation it is clear that as length increases, B magnetic field decreases. Okay, so this is Ampere circuital law. Its equation, that is closed integration of, so it is the symbol of closed integration of magnetic field for any length. Any length means line element of a surface is equal to mu 0 times I, electric current passing through the surface. Okay, so it was case number 1 for infinitely long conducting wire. So this is the equation. Have a look. Got it? Now let us see case number 2. Suppose that wire is converted into a ring, right? So it is for a circular loop, means length of a wire, now it is converted into a ring. So a ring having circumference, right? So instead of length, you have to take, what you have to take? Circumference of a ring. That is circumference of a ring means circle, that is 2 pi r. Means in our previous equation, instead of L you have to put 2 pi r. Here what is r? R is nothing but a radius of a ring or loop. So which was that equation previous? That is B into L is equal to mu 0 I. From this, B is equal to mu 0 I by L, and instead of L you have to put what? Mu 0 I upon 2 pi r. So this is the equation of magnetic field for a circular loop, or you can say that it is for a ring. So it is case number 2. Okay. From this equation, few important points are there, right? So let us see its IMP points. Which are these important points? Let us see. Point number 1. Okay. So in first point, magnetic field B, it depends upon electric current I. Means as electric current increases, that is magnetic field, electric current increases, magnetic field also upside arrow means increases. Got it? Second point. Okay, this magnetic field, that is B, is inversely proportional to the radius of the ring. Means as radius decreases, again magnetic field, that is B, upside arrow means increases, and vice versa. Okay. Third point. What is the third point? Okay, inside the ring there is a magnetic field. So the magnetic field having means B having cylindrical symmetry. Okay, means magnetic field depends upon R radius, and this is known as cylindrical symmetry. Then fourth point, the direction. Direction of magnetic field is tangent to the point on a loop, or you can say that a ring or circle. Okay, so this is about the equation, that is B is equal to mu 0 I 2 pi r for a circular loop. Simple. It is very easy to remember. So what to remember? Simple thing is there, that is to remember first equation, close integration B dot dl is equal to mu 0 I. So it is Ampere's law. Take integration on that side, remove this d, so you will have B multiplied by L is equal to mu 0 I, and this equation is for infinitely long wire, instead of L, if we will take 2 pi r, right, is equal to mu 0 I. So now this wire is converted into a ring or a circular loop. So it is for a loop, right? Simple equations are there. Okay. Now in this video we are also going to cover one simple thing, that is, let us see what is that simple thing. It is nothing but solenoid. Okay, what is solenoid? Let us see. So solenoid is nothing but there is a cylindrical shape and on this cylindrical shape we have to wound the wire like this. So these wires are closely wounded. Got it? Okay. So these are the wires which is closely wounded wire in the shape of cylinder. So each loop means this is the loop number 1. On passing electric current on loop from loop number 1, magnetic field is produced. So each loop having magnetic field, suppose loop number 1 having magnetic field B1. Now the electric current passing through the second loop. So second loop having magnetic field B2. Again electric current is passing through loop number 3. Means in a solenoid, number of turns behaves as individual loop, and this individual loop, the magnetic field having algebraic sum, that is B1 plus B2 plus B3. In short, we can say that the magnetic field of first loop is added into second. The magnetic field of first and second is added into third, and so on. So from this it is very clear that what few points we have to think. What is solenoid? Solenoid is nothing but it is a device. Got it? And this device is used magnetic field of first, second, third. So magnetic field going on increases. So solenoid, it is a device which is used to produce. What to produce? Magnetic field. Right? So this magnetic field is strong and uniform, where it is along the axis. Along the axis means like this, say. So it is the axis of solenoid, and magnetic field lines are passing like this. Okay, so along the axis magnetic field is strong. So along the axis means inside. So we can say that the magnetic field inside means along the axis it is strong and uniform, but outside outside the solenoid outside the solenoid magnetic field become weak. Due to this reason, why? Because B is equal to mu 0 I upon 2 pi r. So according to this equation, as r increases, magnetic field decreases. So as you go away from the center, that means r increases, and because of that magnetic field decreases, right? And from this equation, due to this, we are taking magnetic field is 0. Where 0? Outside. And inside this solenoid, magnetic field, that is B, is how much? Maximum. Okay, so this is about solenoid. Once again, the number of turns of wires which are insulated. So it is the definition of solenoid. If the insulated wires are closely wound in the shape of cylinder, it is known as solenoid. What is solenoid? It is a device which is used to produce magnetic field. Here we have to include few sentences. Again, it is a device which is used to produce strong and uniform magnetic field inside the solenoid. Got it? But outside the solenoid, magnetic field is weak. That is why we have to take it 0. So solenoid inside, magnetic field maximum, that is strong. So it is about solenoid. Got it? Solenoid are of two types. First type is long solenoid. What do you mean by long solenoid? Right? Suppose this is a length of a solenoid, that is L, and here it is its radius of a loop. So what is the long solenoid? In short, you can say that if the length of a solenoid is more than radius of a circular loop. Got it? Simple logic is there. Okay, the length of solenoid is more than the radius of a circular loop of a solenoid is known as long solenoid, and second is short solenoid. What is short solenoid? That means length of a solenoid is less than radius of a circular loop. Either it is long solenoid or short solenoid, the magnetic field inside only becomes strong and magnitude, but either it is long solenoid or short solenoid, the magnetic field outside is always 0. So This is about solenoid. Again, it is used to produce strong magnetic field inside the solenoid. Okay, have a look. Thank you.